power series. So how many of you, just out of curiosity, you really don't need this, but how many of you have taken Calc 2? Everybody, or know the material in Calc 2? Let me rephrase. So you do this thing in Calc 2 called power series. Well, polynomial is finite sum, right? Okay. So these are studied extensively, right? I mean, when you start in algebra 1 in high school, you have a degree 1 polynomial, right? You look at all these lines, right? And then you do parabolas, and in Tennessee, you do that for the next year and a half. And then you do like other polynomials, perhaps, that are bigger. And these are very nice functions, right? I mean, they can be kind of wavy and curvy. The bigger the degree, the more exotic they can look. But you get exposed to this, and Calc 2, somebody said, hey, why stop, right? Well, and here's the problem. This is a finite sum, and you know those crazy analysts, they always make the mistake of trying to plug stuff in for X, so we will indulge them in this talk. If you plug something in for X, no problem, right? You get some finite thing. There's only one thing I can plug in for X, and I guarantee that it's going to be finite. And what's that? Zero. If I plug in 0, you just got the constant term. But after that, who knows, right? So you have to sort of, figure out what does it take for, adding up infinitely many things to be something finite. More generally, you can do something like this. And this is a power series centered at C, right? The difference here is there's one magic number you can plug in for sure that will make this finite, and that's C instead of 0, right? So the first thing to figure out for power series is what is their interval of convergence? And let me put that more intuitively. What crap can you plug in for X that makes this a finite sum, right? So here's the question. So you got to add up infinitely many things and add up to something finite. You already, so I promised you wouldn't have to know much of calculus or anything. I suspect that you all saw this probably couched in maybe in high school. Let me give you an example. Here's an infinite series that I suspect that you all saw before you got to college. For some fixed value of X, you probably saw the series. Anybody know what this series is called? This is a geometric series. Y'all remember doing this? Does anybody remember for what values you plug in or for what values of X will this converge?
Value of X less than 1.
Right, right. If and only the absolute value of X is plus 1. Right. So, for example, you might have had something that you know in high school, like 1 plus a half plus a 4 plus an 8, and so forth and so on. Anybody know what this adds up to?
1 over 1 minus.
That is correct. For a geometric series, it's the first term, which in this case is 1, over 1 minus the common ratio, which is X, because to get every next term you multiply by X. Right? Notice, by the way, let me notice here, these two functions, if you think of them as a function of X being variable, are exactly the same things in this interval here. right? But notice that there are other things that I can plug in here that don't make any sense here. For example, I can plug in -1 here and I get a half. Whereas here I get 1 minus 1 plus 1 minus 1 and so forth and so on. Who knows what that is? I can also plug in 2 here. And if you try to plug in 2 here, you know you're totally hosed, right? Because 1 plus 2 plus 4 plus 8 and so forth. And that doesn't add up to anything finite, even if you are running an engine. So can anybody give an example? So here, what can I plug in? If I want to try to think of this as a function, I can plug in anything between 1 and -1, not including the endpoints, right? Can anybody think of a power series where no matter what x I plug in, it's going to add up to something finite?
One.
Okay, I don't like smart aleck answers. That's actually good. And it's an important observation. If the power series is a polynomial, you can plug in anything. Okay, so what about a power series that's not a polynomial, that actually has arbitrarily large terms in it?
X to the n over n factorial.
Okay, that's one thing to go there. No matter how big of a number you put in for x, those factorials totally kick its butt. And eventually it's very, very small. In fact, so small that I was up to something finite. Does anybody remember how you showed this? From the days of Calc 2?
Ratio tests.
Yeah, the ratio test is really the easiest for this one. As a matter of fact. Anybody know what this function is? It actually is a very familiar function. Let me ask you a question. This is just very intuitive, and since this is just a math club talk, I am going to play it fast and loose. Everybody remember how to take the derivative of polynomials? So there's my calculus thing. Come on, don't sandbag me. Y'all know how to, y'all know how to take the derivative of polynomial, right? Listen, take the derivative of power series, it's just the same thing, right? You do it forever. There's technical things, you gotta be inside the radius of convergence. What happens if you take the derivative of this thing? That's right, you get 0 plus 1 plus x plus x squared over 2 factorials plus x cubed over 3 factorials. And what function do you know that is A equal to its own derivative and B equal to 1 when you plug in 0? Only e to the x, right? So that's kind of big circle, how we know this. By the way, sine x and cosine x both have, you can write them as power series. We'll say centered at 0. Anybody know how to write sine x?
It's the odd powers.
Sort of. Very close, as a matter of fact. So it's basically, as you point out, the odd powers of e to the x, if you sort of extracted those with this alternating minus sign put in, correct? And this is the same treatment. Cosine being an even function, it's got all the even powers. You might check for yourself that when you take the derivative of that first series, this is Take the derivative of this, you get one minus x squared over two factorial plus x five over four factorial and so forth and so on. If you take the derivative of this one, you get minus this one, right? So there's the old formula for the derivative of sine is cosine, derivative of cosine is negative sine. Right? How many of you have seen these? There is, oh, by the way, before I move on to another point, let me ask you this. Let me go to the other extreme. The first example, I can only plug in values of x between 1 and -1 inclusive. These three examples that I give you here, it doesn't matter what you plug in for x, it will always add up to something finite. And in fact, I can sum the series by, for example, if I plug in 10 here, I'll get sine 10. Right, so I'm telling you even more than that. Does anybody know an example of a power series where the only thing you can plug in and it adds up to something finite is 0?
X factorial.
I think, let's see, how about this? This one. See, it's 1 plus x plus 2x squared, which is pretty modest so far. 6 x cubed plus 24 x4 plus 120 x5. No matter how small that you pick the number, if its absolute value is anything bigger than 0, this will diverge. Right, so you can't plug in anything other than 0 and get a finite number out of this. And again, you can verify this using the ratio test if you like. So this is no interesting function. Okay, any questions so far? Does all this look a little bit familiar? Okay, so let me ask you this. Here's kind of a So my next question is this: what kinds of functions So if I walk up to you on the street and I say, okay, I'm going to give you a function here, how can you tell if it's equal to a series or not? Yeah.
What's our domain?
Well, that's going to be part of the question, right? Actually, so let's just what functions equal a series that look like this, and since they're centered at 0, right? Well, the first thing is okay, so let's suppose that I can write some function as a series, right? The easiest thing in the world for me to plug in for this is 0. And so I want to make the observation that f of 0, whatever this first term of my series is, has to be the value of function 0. Well, I can take a derivative of this. And if you believe what I was saying earlier, now if you look at f prime of 0, this is the first term, or I'm sorry, the A1 term, right? If you take another derivative, this is going to be 2A2 plus 6A3 x plus 12A4 x cubed or squared, plus etc. So if you take the third derivative and plug in 0, 2A2. What did I do? 2A2, 6A3 x.
Second.
Oh, am I just a second? Yeah. Let's not take the top. You're right. So now the third derivative, 0 is 683. Anybody see the pattern? Factoid. That's right. Say it loudly. Fn of 0. Looks like it's an. With some funny multiplier, and the multiplier looks like it's in factorial, right? This determines if I can write a power series, say centered at 0, this tells me exactly what the terms have to be, right? A nice little formula. So. So. Let me record a fact. Here, you have a function, and I'm gonna state this a little bit more generally, it's not necessarily centered at 0. Suppose I can write this function that each an is equal to Fn with 7 plugged in over any factorial. And so this thing is called Taylor series. And if I walk up to you on the street and give you a function, you can build its Taylor series. If you have one thing going for it, what do you need to be able to build a Taylor series?
Differentiable.
You need it to be infinitely differentiable. So you need, no matter how many derivatives you take, at the point C, you have to always, it has to be differentiable. Now, just because you can build it doesn't mean it necessarily works, right? So the next question is, it's like, okay, if the function can be written as a series, that's what it has to look like. But maybe the function can't be written as a series. Now, let's just put that to bed for a moment, because most of the stuff that you will ever encounter will be, you can write it as a series, at least on some interval. Let me give you an example here. Suppose I give you this function here. This has no Taylor series. Centered. Right? Because as soon as you try to use that formula, the absolute value doesn't have a derivative in zero. Everybody agree with that? So it's never going to work. It does have a series centered at 1. Anybody know what? Write the series down without looking. Anybody know what it is?
X.
Formally.
Oh.
I feel a little dirty there, right? But I mean, that's what it is. Notice this thing adds up to X, because if you, and actually, since you're centered at 1, this information here is only checking the derivatives at 1. So you're asking this thing to do, you say, hey, Mr. Function, start taking derivatives, tell me what you are at 1. What does it think? It thinks that it is taking derivatives of the function y equals x, right? This Taylor series is exactly right until you, so the Taylor series actually will look like this. The Taylor series actually converges everywhere because it's polynomial, right? And it converges everywhere. And it works really good over here and works really good for a while over here, and then it starts getting bad, right? And the problem is, of course, you've got this problem here at 0, right? Now, what else can we do with series? Well, I sort of hinted this when we had sine and cosine, but you can take their derivatives, right? We got the derivative of sine as cosine, derivative of cosine is minus sine. We sort of convinced ourselves perhaps that, the series I had for e to the x was right because I took its derivative and got itself, alright? So one question is, what is radius of convergence? Next. So this is a natural question that I might ask you. What's the radius of convergence series? So, for example, and let me kind of show you this. I'm sure you know this, but let me show you kind of this pattern here. So we had e to the x was this thing. We had a sine x and a cosine x. I won't write that down yet, but we also had this. And this only held on this range, right? What is the center of convergence of that second series? The center of convergence is always, that's the magic place where if you play, everything drops out except it goes one term, right? The center of convergence is 0, right? Notice this interval is symmetric about the center of convergence, right? With some examples, you have some of the endpoints plugged in and some not, but the actual radius of convergence is the distance from the center of convergence out to the edge of convergence, right? Past one, it doesn't converge anymore, right? That's essentially what, and that's one of the cool things about power series is they're always symmetric, right? By the way, what's the radius of convergence of this one? It's infinity because it converges everywhere. The center is 0 and it goes on forever. Let me ask you this. Here's an application of that observation. What's the radius of convergence of this? This is, what is it? It's 1 plus x plus 2x2 plus 6x6 plus 24. We think. Yeah,
At least one,
how come at least one?
because that's less than n to x to the n.
Okay, good. So if you look at this series, well, let's see, yeah, that'll work. This is 0 plus x plus 2x squared plus 3x cubed plus 4x4. This one is a problem that you might have in Calc 1. This is a simple ratio test. The interval of convergence, this is am I okay with that? By the way, don't try the ratio test with this. There will be a lot of wailing and gnashing of the teeth because the power here on the x is death on a hot plate. Like the factorial here works well, but you've got this really strange power of x. When you take x to the n plus 1 factorial divided by x to the n factorial, you get a difference in factorials, which is problematic. However, the interval of convergence of this is exactly the same. And forget about the one, because that's a finite thing. Notice this piece is exactly like this one, except it's got some missing teeth, right? Everybody agree with that? So everything from 0 out to +1 adds up, not including +1, adds up to something finite, right? Everybody agree with that? This is less than that, so it has to add up to something finite, right? So now I know it converges from 0 to 1. Right? But 0 is the center of convergence, and it's always symmetric. So that means it has to go to -1 as well. And I think it's fairly clear that you don't get the endpoints, right? Because if you plug in 1, this adds up to infinity, and if you plug in -1, it adds up to infinity too, because they're all even powers, right? But okay. So this is kind of an interesting example, because if you try to do the ratio test, it's awful. Let me give you another one. Or here's there we go. And I'm gonna purposely be a little weak. The radius of convergence is the distance from center of convergence to nearest singularity. Now, I haven't defined it. I've been purposely a little bit nebulous here, because I want to show you an example. What's the center of convergence of the series? 0. Okay, now take this function here that I've got a series for, start at 0. Where is the nearest problem point of this function? In fact, there's only one problem, right? It's at 1. So the radius of convergence is actually 1. It's a different distance being sent out here. Everybody okay with me? Now, let me give you something that might make you squirm a little bit if you believe this theorem. I want to find a series for that. Okay, by the way, there's a neat trick that I can use to find a series for this without doing that crazy formula. No, nobody wants to take a bunch of derivatives of this, do you? I don't even want to take the first derivative, much less the nth, right? So can we use this as a tool to get me that? Back to it. Now, there's something that worked better. Next, with x squared minus x squared. There we go. If I replace x with minus x squared, that's what I get. Now replace it in series. Right. Now, here's the thing that bothers me though. You can also do that here. And this is the same thing, right? If x squared is between -1 and 1, that means x has to be between -3 and 1. But what was all that yin yang that I was saying about the distance from the center, which in this case is clearly 0 to the nearest singularity? Where does 1 over 1 plus x squared have a problem? That's right. This thing has a problem at I, so that makes this problem a little bit more complex. So actually, in the complex plane, so you gotta start thinking out of the box here. This is 1 minus 1. This actually has a problem at I. And the distance from 1 is 1 as well, which is again the radius of convergence. Right? So that's kind of a neat trick, because if I walk up to you, I say something like, if I ask you for a Maclaurin's or Taylor series for this centered at 0, then you could certainly do it. I mean, you'd be burning me in effigy for sure, right? Because this gets really bad, right? But you could do it. But I haven't even seen the series. I will tell you that the series that you get for this, that's centered at 0, will have radius of convergence 2, because nearest singular point, right? And that's a little bit of magic, right? Just looking at the function, I can tell you something about that. Let me give you kind of another application. It turns out, as we pointed out before, that you can take a power series and you take its derivative and you integrate it. And miracle of miracles, that doesn't change its radius of convergence. If the radius of convergence is 10, when you integrate it, it's still 10. When you differentiate it, it's still 10. So everybody remember the antiderivative? This is the inverse tangent of x. This is a rather famous theory. And by the way, what does C have to be? Well, let's see, shall we? Because remember, when I integrated this, right, there might be an extra constant floating around. Well, let's plug in, because I am a simple-minded fellow, let's plug in what's easiest to plug in for x, which is 0, because that makes this whole thing drop out. So if I plug in x equals 0, gone, and I get inverse tangent of 0. So I get the inverse tangent x minus x cubed over 3 plus x5 over 5 minus x7 7 9 9 blah blah blah. And this is true by the way. Notice I pulled a quick one. This actually picks up the endpoints, right? Because it turns out, so if any of you have had Calc 2, if you plug in 1 to this, it converges, right? Because you have 1 minus a third plus a fifth minus a seventh plus a ninth minus 11, so forth. Anybody remember what kind of series that is?
Alternating.
It's an alternating series. The terms are decreasing and going to 0, so it has to converge. So you actually pick up, it's impossible for you to pick up anything bigger than 1 because the radius of convergence remains the same. But in this case, you get a little bit lucky and you pick it up. And so, anybody remember what the inverse tangent of 1 is? Power of 4 is equal to 1 minus 1/3 plus fifth minus 1/7, so 9. This is actually a really famous formula because if you multiply this both sides by 4, you get a famous representation of pi. By the way, it's really just, we just look at it and admire its beauty. As far as computing the digits of pi, this really sucks because it's very, very slow to converge, right? It's extremely slow, but it is cool anyway. Okay, any questions? All right, so let me give you an example or two. Here's one right here. Here's some promised applications. This one, I think we sort of saw, this one what we see because it is its own derivative and its value when you plug zeros one. We also have these series. So I'm going to use this to derive probably the most famous, one of the most famous equations in math. And cosine x. It's funny because, like I believe you said that, oh, you know, the sine is sort of the odd terms out of it. So it's clear that there's some kind of relation. There's a big similarity here between the exponential sine and cosine. And let's kind of explore what that is here. Now, we did encounter some complex numbers earlier on, so let's explore that. Let me point out that so I is the square root of -1, right? So you all have seen this, right? You've seen pictures, right? So I squared is -1, I cubed is -I, and I to the fourth is back to 1, and then it cycles round and round again, right? Let's look at e to the ix and just jam it into that series and see what happens. Now, this becomes 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x4 4 factorial plus ix5 5 factorial minus x6 over 6 factorial minus ix7 7 factorial, and et cetera, et cetera. Now notice that alternating, we have real and then imaginary, right? That's what's going on there. So let me pull this apart here. Let me just group them together. Everybody okay with that? And what is this? And this? That's one of the most famous ideas in math, and there it is for you in power series. Now, anybody want to criticize me? I mean, not just clothes, but I did something kind of fast and loose in that.
You just kind of pulled those terms out. I don't know if we can separate those like that.
That's right. If you have a finite sum, you can, what's 2 plus 3 plus 5? It's 10. What's 3 plus 5 plus 2? It's 10. It doesn't matter, right? There are some series that sort of barely converge, and you can rearrange them and make them add up to different things. But it turns out that whenever you're inside the radius of convergence of the power series, you can rearrange things willy-nilly. So for those of you that really want to be careful about this, this is an okay step because the radii convergence of all these series is infinite, so you can turn them around, but you have to be careful in general. Okay. Here's one. I put this one on the calculus challenge one time here. So this might take you back to the Calc 1 days. Sine over 1 minus e squared. What was it squared, wasn't it? No, 2x squared. Maybe even worse. Yep, that's right. Now, this might be something that I would give to a 1060 class when I really didn't like them. Because, okay, so this looks like a L'Hopital's rule problem, right? Everybody agree with that? And it certainly is. You can certainly do it by L'Hopital's rule. And what's the first thing you should do with any limit?
Try and evaluate.
Be like an engineer and be very practical about it and just plug in and see what you get. You certainly get 0 on the top and you get 0 on the bottom, right? And that is a sign from above that there's more work to be done, right? And L'Hopital's rule might be a completely appropriate thing to do here. But let me just take a step or two to sort of dissuade you. So the derivative of sine of blob is cosine of blob. And let's see, that's gonna be what, 30x5 minus, okay, this one's going to be a product rule. So that's gonna be 3x squared sine of x cubed, minus the whole thing, plus x cubed. And then there's gonna be another 3x squared, so it's going 3x5 comes cosine of x cubed. Meanwhile, on the bottom, we have got 3 times 1 minus e to the minus 2x squared times, I guess, 4x e minus 2x squared. I love it. All right, anybody want to keep going with this? There's certainly one thing you could do, right? You cancel this x. Right, this is, nobody wants to do this, right?
Helps a lot.
The answer to this should be minus. Should be like minus a half. I think. Know how to do that. Okay. So. Okay, so sine of 5x is 5x6, and then it's the cube of this, right? Some other crap, right? Higher powers of x, right? Because I mean, the next power is going to be the 18, right? Sine of x cubed is going to be x cubed minus x9 over 3 factorial, et cetera, et cetera. The first term that comes out of this is an x6 plus higher, right? And the next highest term after this is probably the 12th, I guess, right? Something like that. What about down here? Well, e to the minus two x squared should be 1 minus 2x squared plus 4 x4 over 2 factorial, but I don't think that matters. But then it's minus that. Right, and then add 1 to it. So what I've got in the bottom here is what, 2x? I guess it's plus, isn't it? I did minus 2x, didn't I? Yeah, that's right. So this thing right here, I guess is 8 x to the 6, isn't it? Right? Now, if you think about doing a L'Hopital's down, now you've got a complete cancellation of the x6. And everything else is a higher power, right? 5 minus 1 over 8. So, right. Good luck with the L'Hopital's rule, by the way, right? It can be done if you're stubborn enough. But I mean, what L'Hopital's rule basically does is it peels those onion layers off until you get there. You're going to have to do it 6 times, maybe less if you get some cancellation, right? Because canceling that x might reduce like 1 time, but you're going to have to do it a number of times, and it's going to get worse every time. Okay, any questions on that? Here is another one more example. Actually, and I'll give you one to kind of wrap it up. So you might try this for fun. This is kind of grungy, but yeah. Okay, we saw these series before. The derivative of the first is the second. The derivative of the second is negative first, right? But you might wonder, hey, Jim, where'd you come up with this in the first place? Does anybody know a differential equation that has sine and cosine as solutions? Notice, when you take the derivative of either sine or cosine twice, what do? You eventually reverse, you essentially just reverse the sign, right? Derivative of 2 derivatives of sine is negative sine 2 derivatives. So this is another way to think about it. Now, you can solve this differential equation from scratch by assuming a solution of the form write this down, take 2 derivatives of it, put it in there, set it equal to 0, and you will get a recursion relation that gives you both of those formulas. Right? So you can actually work in reverse and start from there. Here's another. How many of you have seen Fourier series? Well, some of you, especially if you're on kind of the engineering or more applied end, you'll probably see it. If you have a series that looks like this, where you have z being a complex variable now, so let's write z as r e to I theta. How many of you have seen this, that any complex number can be written as r times e to the I theta? Probably some of you have seen this before. So Howard series gives rise to this. Let's see, if I take that to the nth power, r n e to the I n theta, which, guess what, is a n r n cosine theta plus I sin, cosine n theta, psi sine n theta. And now you have Fourier series, expansions in terms of angles, cosine and stuff. So I'm gonna wrap this up with one example here. So as I said at the beginning, almost any function that you'll encounter at the beginning, I guess, will be something that is equal to a series at least on some interval. Can anybody give an example of an infinitely differentiable function? And when you get its Taylor series at a point, the function never works. It only works right at the point.
It's like eats the -1/x everywhere except for 0, which is 0 or something like that.
It's close. Where'd you run across that?
Book I read.
Reading. So, yeah, that's good.
Yes.
This function, notice, this function is actually fairly easy to graph. I mean, it's sort of, because as x gets very large, this is getting close to 1, right? So, and of course, it's an even function. But I mean, this thing is so super flat there that if you try to get its Taylor series, first of all, the value of the function is 0, right? So your first term is going to be 0. What's the first derivative? It turns out f prime of x is e to the -1/x squared, and the derivative of this over x cubed. Right? Now notice that the limit of this as x is going to 0, of course, this denominator is getting close to 0, so it's trying to force it up. But I mean, this is exponential, and you know, exponential whoops every polynomial, right? So this goes down to 0, and actually this is 0. And you can keep going. And it turns out that you keep getting these more and more complicated formulas, but the nth derivative of this function, any derivative of this function evaluated at 0 is 0. So here's its Taylor series of 0. It's the 0 function. And notice that only matches this right at 0. This function is never 0 unless x is equal to 0, right? So they are out there deep in the depths of some Stephen King novel. There are these functions that are not equal to this power series, but most of the stuff you encounter won't be true. Okay, there's other applications, but I talked too much. If you're curious about the exponential of a matrix, which I actually was going to add to the talk because I saw it in a talk today where somebody was talking about the exponential of a matrix in a statistics talk. So y'all have a good weekend. Thanks for listening, and stay tuned for next week because we'll have a better speaker. Oh, any questions? All right.